Here's the work from class today. I'm sorry that it wasn't here, but we had meetings this morning. I hope that everything was okay with the sub. Uh, the first couple questions are looking to make some sketches. The sketches we're looking at for the first two are regular log functions. So let's get our axes drawn in. This one, there's no base written. It's log base 10. That number is larger than 1, so we're going to be looking at a logarithmic growth. The minus 6 on the inside means that we're going to shift to the right 6. So that's where our vertical asymptote is going to be. And the graph will be, as I said earlier, logarithmic growth. The x-intercept will be 1 to the right of that, so it is at 7. The second graph, also a log graph. Remember, when you see ln, that's natural log, which is log base e, and e is 2.718. So it's larger than 1, so we're going to be looking at growth. Plus 5 means shift to the left 5 to x minus 5, x equals negative 5. Logarithmic growth, x-intercept at negative 4, 1 to the right. Last one, here we're looking to have minus 3, so we're shifting to the right 3 to x equals 3. It's 4 as the base of the logarithm, so it's going to be growth. But because there's a negative in front, these pictures are going to get flipped over. It's going to look something like that, with an x-intercept, 1 to the right, at 4. Our second set of questions here are looking to convert between exponential and logarithm. We've said before that if you have an exponential problem or a logarithmic problem, the logarithm is always equal to the exponent. The base of the exponent is always the same as the base of the logarithm, and the result of the exponential problem is the input to the logarithm. So here, if we have m to the 5th equals 9, I know that the logarithm will be equal to the exponent. The base of the exponent will be the same as the base of the logarithm, and the result of the exponent is the input of the logarithm. Same idea for b. The log is equal to the exponent. The base is the same as the base of the exponent, and the input to the logarithm is the result of the exponent. We're going backwards from what we were just doing. The base of the log is the same as the base of the exponent. The exponent is equal to the logarithm, and the result was the input. Once more, we know that we are equal to the exponent. The base will be the same, so the base remains 3. The exponent will be x. We are equal to 2. For each of these, we're looking at the same idea. We're looking to take a statement, write it as an exponent, write it as a logarithm. So if the base is 3 and the result is 81, an exponent means I'm taking 3 to some power gets me 81. If you want to know, that answer is 4. In logarithmic form, I know that the exponent is equal to the logarithm, the base is 3, and the result is 81. And that is what a logarithm is asking us. 3 to what power is 81? The answer is x. So here we're saying 6 to some power is 0. This one has no solution. If I wanted to write it as a logarithm, I'd have x equals log base 6 of 0. Again, that says no solution. If I have a base of 9 and a result of 3, what is the exponent? Well, here the exponent will be log base 9 of 3. From what we talked about last unit and previous before that, to get from 9 to 3, we're going to take a square root. That is a 1/2 exponent. If you have a base of 2 and you raise it to a power and you want to get a half, that means we're taking the reciprocal. We're looking at a -1 exponent. Written as a log, the exponent, x, is equal to log, same base, of the result. If you have 3 to a power equals 1 over 27. Again, we're looking at a reciprocal, but this time I want to think about 3 and 27. 3 to what power is 27? Well, 3 to the 3rd is 27. To get the reciprocal, it has to be negative. And I know that as a log, the log will always be equal to the exponent, the base is the same, and the input will be the result of the exponential problem. Once more, if I take 49, I want to know what is the exponent to get 7. That means the exponent is equal to the logarithm, same base, of the result. Here that answer should be, again, like a square root equal to 1/2. This time we're going to convert from logs into exponential problems. So here we have 4 to what power gets me 16. As a note, that power is 2, so t would be 2. I can rewrite this as 4 to some power equals 16. Remember that the exponent will always be equal to the logarithm. The base remains the same, so we have 4 to some power is 16, and as I said earlier, t should be 2. We can check that. 4 squared is definitely 16. Here we're saying some number to a power is 16, and that power is 4. It's a little bit hard to follow just by looking at the log. So let's rewrite it as an exponent. Here, the base of the log is the base of the exponent. What the logarithm is equal to is the exponent. What is inside the logarithm is the result of the exponential problem. Here we take a fourth root. I'm looking for what number can I take 4 times in multiplication to get 16. The answer to that is 2. To be most correct, 2 or negative 2. Last one here, I have 4 to some power equals t. Remember that the logarithm is always equal to the exponent, so 16 is the exponent. The base of the logarithm is the base of the exponent, and it's equal to that result. 4 to the 16th is going to be a very, very large number. If you'd like to, you can plug that into a calculator to get the actual value. For the solving section, these should all be multiplication. I've got a couple examples there. Those are the examples in your packet. So let's look at parts A and B. If I have 2 times e to the x equals 15, first thing I want to do is get e to the x alone. So I divide by 2. I get e to the x is equal to 15 halves. To solve an exponential problem, I'm going to have to rewrite it as a logarithm. To rewrite it as a logarithm is always equal to the exponent. The base of the exponent is always the base of the logarithm. The input of the logarithm is what the exponential problem was equal to. So I get log base e of 15 halves, which we could call natural log of 15 halves because that is log base e. That is something we can plug into our calculator because the calculator has a natural log button on it. So we can see that the natural log of 15 halves is about 2.015. If you want to check your answer, if I take e and I raise it to that power, I should get 15 halves. So if I take e and I raise it to the 2.014903021, and that decimal would keep going, but the calculator cuts it off, we should get something that is almost 15 halves. 15 halves is about 7.5, so we want to get up close to 7.5, and we can see we get very close to that. So that means our answer is correct. Here, for part B, we start in logarithm form. If we're starting as a log, I want to try to write it as an exponential problem. The base of the logarithm is the base of the exponent. What we are equal to is the exponent, because the log is always equal to the exponent. And what's inside the log was the result of the exponential problem. 3 squared we know is 9. We can subtract 4, and we get that x equals 5. So the other thing that's going to come up is we want to make sure we're careful with plugging things into our calculator. So here we're asked for log. If there's no base, it's log base 10 of 125. That's 10 to some power is 125. I know that 10 squared is 100, so it's going to be more than 2, but I don't know exactly what it will be. So it's about 2.097. Then I do log of 5. I know that 10 to some power is going to get me 5. I know 10 to the first is 10, and that 10 to the 0 is 1, because anything to the 0 is 1. So this should be something between 0 and 1. We see that it's about 0.699. And then the last one, if I take my two values, log of 125, close the parentheses, divided by log of 5, close the parentheses, I get exactly 3, which is curious that those other two values were just random seeming decimals, and that this one is 3. What's even more curious is that 5 cubed equals 125, which means that log base 5 of 125 is equal to 3. But we just said that log of 125 over log of 5 was equal to 3, which means that log base 5 of 125 is equal to log of 125 over log of 5. This is what we call the change of base formula, which you can see on the back, on the very last page. So here what we're looking at is that anytime you have a log, you can change the base of the logarithm using this exact formula. So this is useful especially if you're plugging into the calculator, because if we want to have log base 10 or log base e, the natural log, we can make that change happen. So here we have an example. If you have log base 5 of 7, I can't plug log base 5 into my calculator. So what I can do is rewrite using two logarithms, log base 10 or natural log, log base e. The number in the numerator of the fraction in the top is always the input to the logarithm. So here we had log base 5 of 7, so we have log of 7, divided by log of what the base was, so log 5. It doesn't matter if you choose log base 10, log base e, or any other base. It happens to be that log base 10 and log base e, natural log, we can plug into the calculator nicely. I would take a moment right now and make sure that when you plug this value into the calculator that you get 1.209. Make sure you're careful with your parentheses when you enter in these values. For practice, I want to calculate log base 3 of 8. That should be log of 8 divided by log of 3. Again, the base is in the denominator, the input is in the numerator. We can say log of 8, close the parentheses, divided by log of 3, close the parentheses, is about 1.89. It does not matter if you had chosen natural log. It can be any base as long as the numerator and denominator are the same base. We will get a answer that is the same. So about 1.89. Same idea here. Log of the input divided by log of the base. So we do log 5 divided by log 10, which is about 0.699. And then the last one, log 38 over log 5. We get, log 38 divided by log 5. That's about 2.26. If we went back to part 4, question 4 asks us to evaluate any one of these logs. We can check any of these if you'd like to. I'll say we check the first one. So we can say log base 4 of 16. That's log 16 over log 4. In your calculator, we have log 16 divided by log 4. Earlier we said this answer would be 2, and it is confirmed with the change of base formula. Last one, we talked about some word problems last year. We said if something is growing at a rate of 5.2%, that means we have 100 plus 5.2%, which is 105.2%. Write that as a decimal. We can put that in as the base of an exponent problem, where the amount of money you start with goes in front, and we set it equal to what you want to end up with. And now we can solve this question. If we divide by the number in front, divide by the number in front, and we get 4/3 is equal to 1.052 to the t, I can rewrite this as a logarithm, where it's equal to the exponent, and the logarithm has the same base as that, and we input the results of the exponential problem. We can change this into, using change of base, something that we can plug into the calculator. And rather than spending time trying to figure out guess and check or using a table, we can say that this is log of 4/3 divided by log of 1.052, and we can see exactly that it will take 5.67 years for the house to gain that value at that rate. And that is what we had in class today.